All right, the last video of the sequence on rectangular waveguides, we'll talk. First of all, let's sum up a little bit about attenuation and conduction losses. So this is refers back to the previous video, I think number 3, where we talked about attenuation losses due to the finite resistance of the copper walls. And so this is for um, primarily, with the exception of this one curve. This is for the case where A is 2 centimeters and B is 1 centimeter. And we have just copper waveguide walls, and the dielectric inside the guide is assumed to be free space. And so what you can see here is the attenuation as a function of frequency, and you can see as the frequency approaches cutoff for that TE10 mode, you're approaching an infinite attenuation. So this would be when you approach evanescence here. As you get to propagating wavelength, then you see that what happens is the losses drop. They're a minimum here around 20 gigahertz, and then they begin to pick back up. You can see that when you get high enough in frequency, the losses are all quite similar, even though if you look here in the TE11 for this mid-range of frequency, the losses are significantly higher for the higher order modes. But as you approach these higher frequencies, notice certainly the TE20 and the TE10 approach the same value. And then if you look here where we've changed the ratio of B to A, so here A is 10 times B, you can see the losses are significantly higher. So this is an argument for kind of the rule of thumb, the design rule of thumb, why you want your A over B to be roughly 10, or I'm sorry, roughly 2, because that kind of, balances out these attenuation losses that get a lot higher when A gets significantly greater than B. And that's just simply because you have just more conductor there in the direction where you have more surface current, or in the plane where you have more surface current. So anyway, this is just a useful chart to look at, and of course this chart would change if the waveguide shape changed, if you plotted different modes, and if you had a different dielectric. All right, well, let's think about the second type of attenuation, and that's the attenuation due to dielectric losses. Remember here that the dielectric has a complex permittivity, and so the propagation constant in the guide is going to be complex, where beta mn is the propagation constant in the guide for the propagating wave. It's the wave number, so Bmn would be for a particular mode. And then alpha D is the dielectric, so the loss due to the dielectric, so that would be the attenuation constant. So when we look at alpha D, then we see that if we make some approximations for alpha plus J beta, given that this is a low loss dielectric, we get the following expression for alpha on the right and alpha on the left and beta on the right. And we can pull out the expression for alpha in terms of epsilon double prime, epsilon prime, the wavelength, the cutoff frequency in the guide, and the frequency of the propagating wave. So it looks like this. Beta can be written as this second term. So this is your attenuation due to dielectric losses. And I do want to point out that as the frequencies get higher and higher in the microwave regime, we are less likely to have a low loss dielectric and more likely to have a lossy dielectric, because loss of that dielectric increases in a nonlinear way with frequency. So you do need to be sure in using these formulas that you confirm that at your propagating frequency you do indeed have a low loss dielectric. Okay, finally, let's look at some numbers. So if, for example, we look at a copper waveguide that's filled with polyethylene, and we're going to use a standard rectangular waveguide, the WR75, that has A of 1.905 and B of 0.9525. Polyethylene's epsilon prime is given by 2.25. It's a non-magnetic material, so the relative mu is 1. And the loss tangent at 10 gigahertz is 4 times 10 to the minus fourth. So we're asked to find several parameters, including here at the end, the attenuation constants. So we'll go through some of these briefly. First of all, before you do anything else, you always find the wave parameters in unguided media. So you'll find the phase velocity and lambda of the wave with the specified frequency in the dielectric material with epsilon being 2.25. And remember the phase velocity for a low loss dielectric, we can neglect the imaginary part of the relative dielectric constant and just go with the epsilon r prime of 2.25. So when we do that, we get a phase velocity of 2 times 10 to the 8th. Likewise, we can take the phase velocity and divide by the frequency in hertz, and we'll get the wavelength. So the cutoff frequency for the TE10 mode, based on taking the phase velocity over 2a, turns out to be 5.25 gigahertz. All right, now that we know the cutoff frequency, we're able to find the properties of the wave in the guide. So what are the properties of wave? That would be beta, the wave number, that would be lambda, the wavelength, and that would be the phase velocity. And what we do is we just take our non-guide numbers, and in the case of beta, we multiply by this waveguide factor. In the case of lambda and the phase velocity, we divide by the waveguide factor. So you can see then that we get these parameters of the wave in the guide. And notice this is only for the TE10 mode, so we're using those formulas for TE10 and those numbers for TE10. All right, well, the surface resistance of copper can be obtained by using the formula for surface resistance of a good dielectric, which is given here, a low loss dielectric. And so we plug in all the relevant numbers, and we get 2.61 times 10 to the minus 2 ohms, and this is obviously for a unit length. And then we can determine alpha by plugging in the surface resistivity, and then using the formula that we derived or showed in the previous slide with the cutoff frequency for the TE10 mode, and in fact the entire formula is dependent on the cutoff frequency. When you plug all the numbers in, you end up with 0.0163 nepers per meter, which is equivalent to 0.142 dB per meter. So finally, we're going to use the properties of the dielectric to determine the attenuation due to the dielectric losses. That formula is given here, where the loss tangent is sort of the new factor that shows up. So we basically, once again, just plug in the numbers to the formula, and we end up with 0.738 nepers per meter, or 0.641 dB per meter. So when you just solve for alpha directly, you will get 0.0738. And the reason it says nepers per meter is that alpha is actually a term that is in an exponential. So when you have an exponential raised to a power, so like e to the alpha z, e to the minus alpha z, then what happens is you'll get e to the minus, when you multiply alpha and z together, the unit will be nepers. If we then take the natural log of that, the unit comes out to naturally be in dB when we take 20 times the log. So anyway, nepers is the unit that's used when the term is in the exponent, and then dB is what's used when we're expressing it as 20 times the log of a constant loss. So if, for example, you wanted to find the value of the field intensity at some location z, and so I've got a absolute value shown here because, yes, I know that E is sinusoidal in both space and time. It's a traveling wave in the waveguide, but we're just interested in finding the maximum field intensity and how that decays as a function of z. So if we call E sub naught just a maximum magnitude value of E located at a particular space, and we'll let that be in the middle, because for the TE10, that's where the maximum E field occurs. Then basically what this looks like is the electric field is a function of z. The intensity of the electric field is a function of z. Decays is e to the minus alpha d times z times e to the minus alpha c times z, where alpha d My equation editor will not place, if I've already got something in an exponent, it won't place a subscript. So D should actually be a subscript. This is the dielectric um, attenuation, and this is the conductor attenuation. So you can see they're multiplicative. If you were to combine the exponents, they'll be additive in the exponent. Let's go back and look at the numbers. We have 0.641 dB per meter for the dielectric. We have 0.142 dB per meter for the conductor. So in this particular example, the losses from the dielectric are actually more significant or greater than those in the conductor. So, as you can see, you can't really tell until you plug the numbers in and see what comes out.